Welcome to this lecture series in complex numbers. We will continue our discussion on equation of a line, and in this lecture we'll be looking at what is the perpendicular distance from a given point to a given line. Alright, so let us recall basically what we have seen so far in that context. So if w is non-zero and r is a real number, then the set of all the complex numbers z that satisfy this equation is a straight line. Alright, here are some related problems. The first problem asks to find the equation of a line which passes through two given points. And the second asks for necessary and sufficient conditions as to when two given lines, two given equations represent the same line. All right. So here is a simple lemma. So suppose w is a non-zero complex number and r is a real number. Then the distance from the origin of this line is this number. So this is the origin, this is our given line, and this is the claim. So basically we have already done this. The reasoning that we gave to show that this is indeed an equation of a line is exactly what will give us that number. So let's recall that. I will be arguing under this assumption that mod w, meaning the magnitude of w, is 1. And the general scenario I'll leave as an exercise. Alright, so what does this say? W bar z plus wz bar plus r equals 0 implies twice of real part of w bar z is minus r, which implies real part of w bar z is minus r by 2. All right. So the things which satisfy that, if you rotate them by w bar, meaning if w is cis theta, then if you rotate things which satisfy that by theta in the clockwise sense, you get that their real part is this number. So after rotating, this number, this is minus r by 2, is all those complex numbers that were initially here. So this is the initial line and this is the rotated line, and therefore distance from the origin is absolute value of that real number, which is r by 2, or rather mod r by 2. And since w had magnitude 1, this is nothing but r by twice of w absolute value. So that's the proof. All right, so just there's a very simple way to detect the distance from the origin of a given line. Okay, so all we used was the fact that w bar just causes rotation by theta in the clockwise sense. If w is cis theta, then w bar is cis minus theta, and hence it just induces rotation in the clockwise sense, and that's it. And now let us find the formula for the general, distance from a given line to a general point, not necessarily the origin. Again, w is a non-zero complex number and r is a real number, and we have fixed a point z0 in the complex plane. Then the distance from z0 to a given line, which comes from w and r to this given line, is this number. It's the magnitude of this particular complex number. And again, I will argue under the assumption that this is the case. One can easily generalize. So the point is, suppose this is our line. This line is this is the line whose equation is that. So let me call this L. This is the line L whose equation is given to us, and we need to find this distance. So the idea is, or the preliminary idea is, that we may make z0 the origin. So this becomes the origin, and then we just find the distance from the origin of this given line. Right, and then we can just use the previous slide. So we will execute this. Basically, instead of translating the coordinate axis to this point, we will just translate the line. Okay. So what we will do is we will translate this line by z0 in the negative direction, meaning we will translate this by minus z0. So that's what we will do. And let me draw a picture. So copy. So this is the translated line, and we are interested in this distance. Okay. So note that. Basically, what we need to now do is find the equation of this line. This is what we need to do. Once we find the equation of this line, we can just use the previous formula and find the distance from the origin, and the distance from the origin is precisely this distance. Right? So that we realize, and let me call the translated line L prime. Right? So Z in L prime, if and only if Z plus Z naught is in L. Right? This was obtained by translating L by minus Z naught. So something here, or some point is here if and only if you add Z naught to it and you get something on L. So these two things are equivalent, and therefore this happens if and only if W bar Z plus Z naught plus W Z bar plus Z naught plus R equals 0. Let me shift it a little bit. Yeah. So this is if and only if W bar Z plus WZ bar plus W bar Z naught plus WZ, sorry, this was a bar here which I missed. So this was a whole bar, and hence this is that. WZ naught bar plus R equals 0. And this is a real number. Why? Because this is a real number and that is a real number. And therefore, the distance from the origin, or even before that, the equation of the line L prime is therefore this. Z lies in L prime if and only if it satisfies that equation, and hence the equation of L prime is that. And now the distance from the origin of this particular guy is this divided by twice of, I did not even need to assume that mod W is equal to 1. This is divided by twice of W absolute value. I'm just using the previous proposition. I proved the previous proposition only for mod W is equal to 1, but I will use the generality of the previous proposition. So I'm just using this formula. So this is your real number. This is 2 and this is W. An absolute value, which is precisely what we see here. And that's it. So it's a very simple proof if you just look at it right. Another way to do it is, you just write Z as x plus iy and then get medieval with it. You get a linear equation in terms of x and y and apply basic coordinate geometry. There's a formula for the perpendicular distance between a point and a line in coordinate geometry, and you can use that. But I think this is much more straightforward and much more natural rather than some stupid computation. All right. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.